7.6 billion. That's the number of people that inhabit our planet. Most people wake up, go to work or school trying to get an education and make a living. We stress about our grades, our career prospects, how much money we make. Is there enough of it to feed my family? And right there is the big question. The biggest worry that you might face. Can I feed my family? By 2050, the world population is expected to be 9 billion. These 9 billion people need to be fed, yet even today, 1 billion people globally are starving, while 1/3 of global food production is wasted. According to the UK Cross-Government Programme on Food Security Research, in the next 35 years we need to produce more food than we have done in human history. Food production needs to increase by 60% to meet the expected demand in 2050. This challenge is intensified by a number of other factors. Firstly, the world's growing population is becoming richer, and richer people tend to eat more meat and dairy, which is resource intensive to produce. Then we need to find where we're going to grow this extra 60% of food. An increasing population means an increased demand for housing, and we are already experiencing higher rates of urbanization. Add to that the current and future climate change effect of rising sea levels, as well as the land needed to create bioenergy and to try and capture and store carbon. There doesn't seem to be any land left for additional agriculture. The only option then is to increase the output sustainably of the land already being used. But how do we achieve this? Here at the University of Sheffield, Professor Duncan Cameron has made some exciting developments. His work looks at how relationships between plants, fungi and bacteria in the soil could provide some solutions to the food security challenge. He says it's like listening to plant chatter.
80% of all plants that currently live or have ever lived have an intimate symbiosis with a fungus, and the only way they can survive and take up the nutrients that they need from the soil is by giving energy from photosynthesis. So plants make sugar, they give that sugar to the plant, it uses that energy source, and the fungus goes out into the soil and it can access the tiny little pores in soils that the plant roots are just too big for. And of course fungi have completely different chemistry to that of a plant, so they can chemically take up and release nutrients in a way plants can't.
However, Professor Cameron's work has revealed more to the story. He and his team have identified a 4-stage process which results in the relationship causing the plant to be more resistant to disease.
So I developed this 4-step model, which has basically been the foundation of a lot of my research since, in terms of understanding that relationship at the immunological level. So effectively, when you're a beneficial fungus, you come into your host plant root, and your host plant has to defend itself because it doesn't know at that point if you're friend or foe. So the plant recognises characteristics of the fungus. We call those MAMPs, and these are the kind of patterns on the surface of microbe cell walls, the molecules that they're made of that stick to them, that allow the plant to recognise that another organism is inside it. And when it does that, all hell breaks loose. The plant's alarms start ringing and it starts to defend itself. Now, what I'm really interested in is the process that then follows when those two organisms start to talk to each other and they send each other signals, effectively, hey, what the hell are you doing here? Don't worry, I'm your friend. And those signals can then cause that local defense to turn off, which is great, so the symbiosis can develop. But like us, when we get infected locally by something, we can have a whole system response. So when plants recognise a pathogen, one of the first things they do is send signals throughout their body to say, hey, I might be being attacked, get ready. And the legacy of that then means that even this mutualist, this beneficial fungus colonising the plant root, the legacy of that interaction can leave the plant in the primed state. So as soon as it's in this primed state, it's better able to defend itself against pathogens. When these symbioses start to form, they don't just change the signals that they send to each other, they change the signals that the plant sends out into the environment as a whole. So the way a plant recruits a beneficial microbe is by, again, talking to it using chemistry, and it sends signals out into the soil to say, hey, come and find me, which will cause bacteria to swim towards the roots and to reproduce within the rooting zone to help the mycorrhizal fungus break down the nutrients. But of course those are bacteria, they might be harmful too. So the plant goes through this same process of preparing its immune system for attack. So you often see this, what we call synergistic effect, where the priming of the plant defences is simply more than the sum of its parts. The plant is more ready to defend itself than it would if either one of those two organisms had found its way into the roots.
So, how does this research help? Estimates suggest that losses from disease-causing pathogens, pests and weeds account for anywhere from 20 to 40% of global agricultural activity. Current methods to reduce these losses include using pesticides and herbicides. However, they only add to the problem. They are expensive, contribute to pollution, and are generally unsustainable. By using this mechanism of induced resistance in plants, we can sustainably make plants more resistant to disease. This will reduce global crop losses and take us a step closer to making sure there's enough food on the table in 2050.